section 2.8 about function operations and composition, we are going to move on to compositions. So what a composition of functions does is it takes an input and it puts it into one function. Then the output from that function goes into a second function, and then finally you get your ending output. So we have an example here. Well, let me tell you how we read it. We read this f of g of x, or f circle g is another way to write it. I tend to say f circle g or f of g. I almost never say f compose g, but that's the correct way to say it. The domain is going to be, I will talk about that on the other page. Don't worry about that right now. Here's a real life example of how composite functions happen. Consider the following retail situation. There's a $40 pair of blue jeans that's on sale 25% off, but if you purchase them before noon, they're an additional 10% off. So what is the final sale price of the jeans? We might be tempted to say that the jeans are 35% off because it's 25% and then an additional 10%, which would make them $14 off, so $26, but that is not correct. Because what's actually happening is we're going to take the original price of the jeans. The first function takes 25% off, which makes the jeans $30. The second function takes 10% off, which makes the jeans $27. So you have to do these composed functions in the correct order. If we would have done the 10% off first, we would have gotten the wrong answer as well. So you got to go in the right order, and you can't just put the two together and then do it. So here is an example evaluating a composite function. It's far easier, I think, if they give you numbers. So that's what we're going to start with, and then we will work to when we just have variables, which is a little bit more, I don't know, a little less easy to do, I think. So in this example, f circle g of 2, that means f of g of 2. So when you're working with these functions, you want to start from the right basically and work your way left. So the 2 is going to go into the function g of x. So 2 goes into g. I have to figure out g of 2 first. G of 2 would be 4 over 2 minus 1, which is 2. Well, that's unfortunate. So the 2 goes into g. What comes out of g is a 2. And we put that into f of x. So g of 2 was 2. So I replace g of 2 with 2. And then I find f of 2. F of 2 would be 2 times 2 minus 1, which is 3. So 2 goes into g, 2 comes out of g, 2 goes into f, and then the final answer is 3. Hopefully this one will be a little less repetitive. So what we're going to do, another way to write this, g of f of negative 3. So this time our inside function is f. So that negative 3 is going to go into f of x. So f of x is 2x minus 1. F of negative 3 is 2 times negative 3 minus 1, which is negative 7. So negative 3 goes into f of x. Negative 7 is the output, which becomes the input for g of x. So the next thing I need to find is g of negative 7, which would be 4 over negative 7 minus 1, or negative 1/2. So the output at the end of it is our answer, which is negative 1/2. To find the domain for a composite function, so now we're going to move on to just using variables. So we have to be able to find the domain after we're finished. To find the domain for a composite function, we're going to have to look at two different places. We're going to look at the domain of the input function and the domain of the final function. So the domain of the input and the domain of the final, and then we're going to look at the intersection of those two domains. So in this example here, f circle g of x, another way to write that is f of g of x. So which one of these is our input function? What's the one on the inside? So this is our input function. So I need to find the domain for g of x. G of x was 4x plus 2. Remember that for domain, we really only have two things to watch out for. Domain, when we have an even index radical, we're going to set the stuff inside greater than or equal to 0. That's one of them. The other one is when we have stuff in the denominator and we take that out of the denominator, set it not equal to 0. Those are our two domain things we have to watch for. In g of x, neither one of those is happening, so the domain for g of x, which is our input, is negative infinity to infinity. Now we're going to do f of g of x. So that means I'm going to take g of x, which was my input, and I'm going to replace the x in f of x with whatever g of x is. So f of g of x means f of 4x plus 2, because that's what g of x is, which means replace the x's in f of x with 4x plus 2. So that will be square root of 4x plus 2. So this is the answer to f composed with g of x. It's square root of 4x plus 2. But then we have to find the domain. The domain, we have to consider the input function, which we just did, is negative infinity to infinity, and the final function. Well, the final function is this answer right here, and it has a radical. So I have to take the stuff that is inside the radical and set it greater than or equal to 0. So 4x plus 2 is greater than or equal to 0, which makes 4x is greater than or equal to negative 2, or x is greater than or equal to negative 1/2. So I have a domain that's all real numbers. Combine that with a domain that says greater than or equal to negative 1/2, and we're going to end up with a domain that goes from negative 1/2 to infinity. So the domain for my composed function would be negative 1/2 to infinity. Let's look at g circle f of x. So now we've got to go backwards. G circle f of x means g of f of x. Well, this time f of x is our input because it's the one on the inside. So our input function, f of x, is the square root of x. What is the domain for square root of x? Well, it's one of our parent functions, so you might remember it from doing section 6, I think it was. Or you could do it algebraically. I have a square root, so I need to take what's inside the square root, set it greater than or equal to 0, which gives me a domain of 0 to infinity, including 0. Now let's do our composition. G of f of x means we're taking g of x, which was 4x plus 2, and replacing the input with f of x. F of x happens to be square root of x. So I'm looking at g of x. I'm going to replace this letter x with whatever f of x is. So I have 4 times the square root of x plus 2. This is the answer for that composed function. G circle f of x is 4 square root of x plus 2. And then we have to find the domain. The domain for the final function, it has a square root in it, so I'm going to take what's inside the square root, set it greater than or equal to 0, and that's actually the same domain as the input function. So the domain would be 0 to infinity. Let's see if we have more examples to look at. Indeed. F circle g of x. F circle g of x means f of g of x. So in this case, my input is g of x. So I need to figure out the domain for my input. G of x is 1 over x. That domain, I take the denominator, set it not equal to 0. So that is my domain restriction. Now let's do f circle g of x, which means I'm taking f of x and replacing the letter x with whatever g of x is. So f circle g of x would be 6 over, replace that x with 1 over x, minus 3. Now I can't leave it looking like that because it's weird. So I am going to fix the weirdness by multiplying each term in the numerator and denominator by that denominator of x. That's going to clear things up. So then that's going to give me 6x in the numerator, and the denominator will be 1 minus 3x. This is going to be the answer to f circle g of x. That's the function. Now let's get the domain. So for the domain, I have to consider the input domain and the final function domain. So in this final function, I see I have stuff in the denominator. So I need to take 1 minus 3x, set it not equal to 0, and I will solve that equation and get x cannot equal 1/3. So now I know x can't equal 1/3 and x can't equal 0, but it can be absolutely any other number. So I will have for a domain from negative infinity up to 0, skip over 0, go from 0 to 1/3, skip over 1/3, and go to infinity. So this will be the domain for that composed function. How about g circle f? G circle f means g of f of x. So I'm going to find my function g of x, and I'm going to replace the x right here with all of f of x. So g of x was 1 over x, so 1 over, replace the letter x with f of x, so 1 over 6 over x minus 3. Okay. Again, I have this little stacky fraction that I need to fix by multiplying by x minus 3 each term. So that is going to be x minus 3 in the numerator and 6 in the denominator. So this is the result of g circle f of x. That's the answer. Now we need to look at domain. So remember, for domain we need two parts. We need to look at the domain of the input function, which in this case was f of x, and the final function. So f of x was 6 over x minus 3. The domain for that, I have variables in the denominator, so I set the denominator not equal to 0. So this is going to be x cannot equal 3. The final function doesn't have any denominators with variables, doesn't have any square roots with variables, so the domain of my finaling function is all real numbers. So combining those two together, all real numbers with x cannot equal 3, that's going to give me a domain that goes from negative infinity to 3, skips over 3, and goes to infinity. I think we get one more practice here. We're supposed to show that g circle f and f circle g are not the same. I mean, we did just see that they are not the same in the last couple of problems we did, but we'll do that again. So we want to show that g circle f and f circle g are not the same. Okay. G circle f of x and f circle g of x. Okay. G circle f means I'm going to take g of x and replace the x with f of x. Okay. G of x is 2x squared plus 5x. So g of x actually has a couple of x's this time. right here, and right here. So I'm going to replace this x and this x both with 4x plus 1 because that's f of x. So I'll have 2 and then replace the x with 4x plus 1, and that is still squared, plus 5 and replace the x with 4x plus 1. Now let's reverse that process over here. F circle g means take f of x and replace all the x's with the g of x function. F of x only has one x, it's right there, but I'm going to replace that x with all of g of x. So f circle g would take the function 4 times x plus 1 and replace the letter x with 2x squared plus 5x. So 4 times that replacement plus 1. If they wanted me to multiply all of this out, I could do that. I would need to box multiply 4x plus 1. So that would be 2 times 16x squared plus 8x plus 1 plus 5 times 4x plus 1. Then distribute. So that's 32x squared plus 16x plus 2 plus 20x plus 5. And then combine like terms. So I end up with 32x squared plus 36x plus 7. So that's G circle F. F circle G, I distribute that 4. And there are no like terms. So F circle G is this, G circle F is that. And we have now shown that they are not the same thing. Occasionally they are the same thing. They are going to be the same thing if the functions are inverses of each other for sure. And there may be other times, but that's the only one I can think of off the top of my head. All right, so let's work backwards. So we're supposed to find functions f and g such that when I compose f circle g, I get this function. So I first need to know what's my input function. So in f circle g, that means f of g of x. So g of x is the input. That means I'm replacing the letter x with some function. There's a couple of ways that you can do problems that look like this. One way to do that is to just take the whole chunk that you see inside something, like x squared minus 5 is inside 2 sets of parentheses, and I could use that as my input. Right there. So I could say that g of x is x squared minus 5. And then when I figure out what f of x is, I just replace everything I just underlined with the letter x. So f of x would be x squared minus 4x plus 3. Or I could go even further inside. So I could look at like inside and make the replacement that the input function g of x is this x squared right here. If I do that, if g of x is x squared, then I'm just replacing what I just took out with the letter x. So then f of x would be, replace that with an x, parenthesis, x minus 5. Oops, you guys, that was cubed. My bad. I can't read. That guy was cubed right there. X minus 5, because I replaced the x squared with an x, cubed, minus 4, and then x minus 5 plus 3. And I switched my colors. But there are two different options that you can do for those replacements. Here's a couple more examples. Just don't think too deep about these. Just kind of go with it. So f circle g of x. Find an inside. So one option would be to make it 2x plus 3 for g of x. So if g of x was 2x plus 3, then f of x would be replace 2x plus 3 with just x, cube root of x minus 4. But what if I made g of x equal to just 2x? Then f of x would have to be the cube root of, replace 2x with just x, so cube root of x plus 3 minus 4. But what if I made g of x the whole cube root of 2x plus 3? So the whole thing, that whole cube root. Then when I make my replacement, f of x would just be x minus 4. So there's 3 different possibilities on that one. Let's try this one. F of g of x. If I made g of x x squared minus 1, then f of x would be, replace x squared minus 1 with just x, would just be square root of x. But if instead I made g of x x squared, then when I take x squared out and replace it with x, f of x would be square root of x minus 1. So there's lots of different possibilities. I think on MyMathLab it'll be like multiple choice, and if you had a question on a test like that, I would accept any of those correct answers. The one thing you can't do is just make your inside function regular letter x, because then that's not really making a replacement.